Yeah. So that was a great first talk. Now for a second talk, we have cache tactics, optimizing performance with smart eviction strategies. Obviously, cache optimization plays a very major role in performance. And for a speaker, we have Anamika Roychowdhury from IBM. So please, ma'am, please. Uh, is it on? Where's the mic? Okay, I have to give that to her. The clip-on mic. Give to her. Yeah, Dhruv, give your mic. I have to go between rounds, so she will switch this on. I'll switch this off. Yeah, just switch that on.
Yeah, good morning everyone. I'm Anamika Roychowdhury from IBM. So I am working for IBM in memory distributed cache for a long time, and like this product has like a lot of customer over the globally, and we actually help the customer deciding their different cache statistics and strategies. Yeah. So I'll just start. The agenda for today is like what is cache, and then the benefits of caching, and the different types of caching and its use cases, and then cache eviction and the different the matrix, the cache matrix, and what to consider when we actually select one eviction strategy for a particular application. What are the different things we should consider? And then I'll talk briefly about the most important and well-known caching algorithms like LRU, LFU, clock-based eviction, their pros and cons and their use cases. And then, as we know, like FIFO is very well known, but it is actually not good for caching. But can FIFO be a future? And then some of the eviction strategies on FIFO-based algorithms. Okay, so yeah. Caching is a system design concept that involves storing frequently accessed data in a location that is easily and quickly accessible. So the main importance of caching is reducing the response time and thus increasing the performance and efficiency of a system. So in today's digital worlds, it is very important that the success of an application depends on how scalable it is. How can in their high demand, how can it performs well? Okay, so a system is scalable when it actually works properly without any crash when in case of high demand, and caching comes into play here. I just want to give an real life examples. Like I have gone to a HM store one weekend during festivals and to buy some clothes, and I have chosen some clothes, and then I headed to the billing counter, and then I saw a very big queue, and everybody was looking very annoyed because and then I come to know that there is an offer going on, and that's why there is lot of requests to their system, and the billing system has crashed. So yeah, so think about this, the user experience here. So if they have their application have been designed with the best caching strategy implemented, then it could have actually able to perform well during this high.
Can you share the full screen?
Yeah, sure. Okay. Okay, so yeah, so during this high demand, it could have been able to perform well. So thus, with the faster data access and reduced latency, caching can improve performance and can manage spike by scalability. Okay, and then in computer science, you have seen that caching is a very important concept, and everywhere it is used, starting from hardware till like every layer of our application architecture. Like hardware cache, you can think of like CPU, L1, L2 cache, and then you have memory, disk cache, page cache. In the web browser, you have browser cache, and then content delivery network like CDN, which actually delivers static content of images and videos. That there we use caching. And then in our application server, there also we use caching to get the data fast. Okay, so in a typical application architecture, like every layer, you starting from client application, going to the load balancer, content delivery, API gateway, message broker, everywhere, even relational database. Inside database also we use caching. Like we Bufferful, a database management manager actually creates a special covers a special area in the main memory which is called buffer pool, and it actually cached all the previously computed result to deliver it first. Okay, so everywhere like we are using caching. So how important caching is for the system design? So, but cache is a very small it is the storage is costly, so you cannot use a very big storage for caching, right? So you have to use the storage very thoughtfully. So and that's why eviction comes into picture. So you have to evict the data so that cache only contains the most relevant and important data in the cache. So yeah, and then for that eviction to works well, we have eviction algorithms. So actually eviction is kind of a crystal ball, right, which we can see through the future, and you should be able to tell, okay, this data will not be needed in the future, so I will evict it. So which is not possible in real world. So that's why it is hard, and that's why there is lot of research going on in this eviction policies. And it is still, it has started long back, and it is still going on. Yeah. So then how can we tell that one eviction algorithm is best for an application or for a scenario? And for that we need some metrics, right? So cache metrics. So there are 3 metrics, like efficiency like what, like if you try to access a data from a cache, that means and you are able to get that data from the cache, there is a cache hit. But if you are not able to get the data, that is a cache miss. So how efficient the cache is depends on their miss rate. If the miss rate is less, then cache is more efficient, and if miss rate is more, then it is not efficient. And then throughput, like how many applications at a concurrently it use the cache. So if you think that efficiency, if a cache is efficient, then it must be throughput. Its throughput also will be good, but it is not the case. Why? Because it comes, the caching algorithm implementation also comes into picture. You think that if your caching algorithm implementation is very complex and it is not scalable, let's say to implement the algorithm, to do the computation, it needs to take a lock. Okay, so then it is not able to scale properly. So that also comes into picture here. Okay, so while deciding this caching eviction algorithm, what are the different things we should look at? Like we have different workload, right? Like web cache has different types of workload, distributed caching has different types of workload, and we have a different access pattern. Like some of the access pattern is loop pattern, and then some we will talk about it later, which is a very nice concept. Like some of the workload has power law like Gaussian kind of a distribution. Okay, and then also we should consider, like in a CDN cache, there are multiple layers of cache, not only one single layer. So depending on which layer of caching you are implementing, what kind of workload and access pattern you are trying to address, and depending on which kind of cache matrix you want to achieve, and including all these factors, we will decide our caching algorithm to be selected. Yeah. So then first thing is like which always comes into our mind and which is very simple is FIFO, first in first out. So what the item which has been inserted first will be so the first, the oldest item gets removed to make the space for the newer items, and it is pros are it is very simple. It does not gives any biasness to any items. It is fair, and it has a very predictable behavior. But most of the cases it does not work well because the real work access pattern is not like FIFO. So because it does not give it does not think about the popularity. Like some of the items are more popular and most of the other items are not that popular. So it does not consider that. So that's why it gives very poor hit rate. So it is not efficient. And the use cases of these algorithms are scheduling algorithm in operating system, message queue, then streaming application, like where it is very good for the stream kind of a data. Data is coming and going, and like it's always new data is coming. Okay. Yeah. So then comes like random replacement, this is also very easy to implement. You just randomly choose one data and then just evict it. Okay, so it is very simple and it low overhead. It also avoid bias, but it gives very suboptimal performance because there is no adaptability. It does not adapt according to the access pattern. Okay, so that's why sometimes it by chance it can give a good hit rate, but most of the time it gives poor hit rate. Okay, so yeah, if something is not critical like caching environment, like if you get a cache miss, it does not depend much. In that kind of scenario, you can use it, and then some testing simulation you can use it. Okay. And then comes the list recently used. So the idea is just evict the data which don't evict the data. Evict the data which has been used, which have not been used for a long amount of time. So the idea is here it takes into consideration that the data which has not been used for a long amount of time will not be used in the future. Okay. So this is also simple and efficient, and it is very well known. Many places we use it, but it actually adapts to the access pattern. Okay, so but you can see clearly that it gives a strict ordering of the elements. The way the ordering of the elements actually in that order only the elements gets evicted. Okay. But to keep that strict ordering, like whenever it has to get the lock of the queue and then change the ordering. That's how it is not scalable. Okay. So but yeah, it is used in most of the important caching places like web caching, database management, file system. Okay, and then comes the least frequently used algorithm. It removes the least frequently accessed item. Okay, so it as LRU gives important to the temporal locality, and then LFU actually thinks that okay, the data which is not being used frequently will not be used in the future also, and data which is being used frequently will be used in the future. So think about a scenario like some post has gone viral, okay, and many users are actually looking at the post, and there are a lot of like these data are getting accessed very frequently, but after some time it will not be like after some hours it will not be accessed much, it will not become that popular. So but still it stays in the cache because it's already got a very big high frequency. Okay, so but it is staying in the cache, but it will not be accessed in the future later. So that's why with LFU, if we add a aging kind of a concept, like okay, not only frequently accessed but also we put a aging. Okay, you have stayed in the cache for so long time, though you are frequently used, so you will be evicted soon. Yeah, so in database querying, network routing, content recommendation, we use this kind of caching. And then, comes that LFU and LRU together. This is a hybrid caching algorithm, so it takes the combination of benefit of LRU and LFU both. So you start and then you check whether there is a 2 queue, LRU and LFU, and then if you start with the LRU cache, and if it reaches the number of frequencies to a certain threshold point, then you actually remove the data to the LFU cache. And then and there is also a TTL associated with each element. TTL means time to live. If you have stayed in the cache for so long time, then you should be evicted. So you start and then check whether it is there in the LRU cache. Yes, okay, then fine. And then you increment the counter of the frequency. And if that counter reaches some threshold point, then you actually insert that data to the LFU one. Okay, and then if the cache is not there in the LRU cache, then you go to the LFU cache. If it is there, you reset the TTL. And if it is not there, then you insert the data in the LRU cache. Yeah. So this actually, this is superior over individual LRU or LFU because in heat terms, because it actually takes the benefit of LRU and LFU both, but it is little more complex to implement. Okay, then we have a segmented LRU. Segmented LRU, like it is kind of a LRU LFU only, but here also we have 2 queues, but instead of one LRU and LFU, we have 2 LRU cache, and one is probation segment. So in the probation segment, if it is like young age, if you are getting accessed multiple times, then you move to the protected segment. So it actually takes it consider the temporal locality, like how recently you have been used, and also it takes that, okay, how frequently you have the data has been used. Okay, and then there is something called clock algorithm that all of you know, like second chance. It is approximation to LRU. LRU is not scalable because it has to keep the strict ordering of the elements. So this algorithm is very simple. You have a reference bit to each of the element. And then whenever you get access the element, the reference bit is set to 1. Okay, and then there is a hand which moves clockwise and select which element will be evicted or not. Okay, so if he sees that, okay, while moving the hand, if he sees that, okay, the reference bit is 1, that means it has been used once. That means let me give the second chance because it might be used in the future also. So it will not evict that data, and then it will move around, and then whenever it sees the reference bit as 0, then it evicts that data. Okay, so this is widely used, and it is an approximation to LRU, but it is very scalable because it don't needs to keep the strict ordering of the elements. Okay, so now let's talk about real world how the access pattern is. In most of the cases we use caching is wave kind of a workload. In wave kind of a workload, we have it follows Diffeon distribution, power law distribution. Let's talk about something called one-hit wonders. So in most of the cases, the data which is being accessed will not be used in future. Those are called one-hit wonders. And in real web-based cache, so there are lot of one-hit wonders. So what does it mean? Power law distribution is that the number of elements which are getting accessed more than once, it's much less than the number of elements which are getting accessed only once. So most of the elements, only few, maybe 20 or 30% of the elements are there which are popular, which gets accessed more than once, and rest all 70-80% elements are all accessed only once. So in that kind of workload, actually LRU does not do well. Okay, so that researchers had thought about it, and why not use FIFO? because FIFO is very simple and it has fewer metadata, less computation, more scalable, because you don't need to keep the strict ordering of the elements, you don't need to acquire any log. Algorithm implementation is very easy here. So so then they thought of thinking about what can we trick in the FIFO so that we get better performance here. In context to that, let's talk about something called eager promotion and passive demotion. Okay, so in LRU kind of a technique. Okay, so in LRU kind of a technique, so we have it is eagerly promoted. So whenever an item is getting accessed, it is again put it back to the first, like more preference. Like so every time we are promoting eagerly, but we are not demoting. Like we are doing passively demotion. Like we are not evicting data in that way. So that's why it is not able to perform well in that kind of a workload. So, in case of FIFO, FIFO reinsertion. So, if we just reinsert, like we evict, we promote a element only during eviction. When we are trying to evict, then only we do a promotion. So that is like lazy promotion, but when we actually quickly demote, we evict the data very fast. New data coming in, we are checking that, okay, whether that has been accessed again or not. Not accessed, evicted. Not accessed, evicted. But when we actually evict and we see whether any item has been accessed twice or not, and then we actually promote it. So that is called quick promotion and lazy demotion. So so with that, with that FIFO reinsertion, we have a S3 FIFO algorithm. There are many other sieve and all these algorithms which is on FIFO. There are some modification of FIFO, and then which follows the principle of quick demotion. I just don't want to go to the like implementation of the algorithms. So, but this is just a thought that, okay, in those kind of workload, let's use FIFO and some alternatives of FIFO with the FIFO reinsertion, and we get much better performance. Yeah. Thank you.
Thank you for the great talk. Any questions, please raise your hand.
Thanks for the talk. When you said, I understand from the hardware cache that there is a limitation of the size because it's the first access from the CPU. But when we talk about a software cache like a web cache, what is the constraint that we have that we'll have to have the less size for the cache?
Yes, because we even web caches save the data in some place, like some storage. The caching storage is much faster than main memory. This storage is much slower to access and less costlier. But caching storage, we have to, like, for a distributed cache, we store the data in the main memory. Main memory is much more costlier than the disk. Because caching has to maintain low latency. You have to get the data very quickly. For that, storage cost is more. The kind of technology it uses to store the data, it is more costly.
Anyone else? Anyone else has questions? Okay, thank you.